Another, and I think perhaps more troubling for the many worlds theorist problem, it relates to probability. So I guess first, why is probability something that the many worlds theory in particular needs to grapple with? You point to a number of issues. One problem is incoherence, no relation to decoherence, and then the other is the quantitative problem. I think maybe we can just start with incoherence, which if I understand correctly, is simply the question of where probability fits into the deterministic story told by the Everettian theory. And I don't even know if we've explicitly mentioned that the theory is deterministic.
Right, yes. So quantum mechanics is deterministic until you make a measurement. And in the Everett interpretation, measurement is just one more physical process. So it's deterministic all the way through. But the tests we make of quantum mechanics are explicitly probabilistic. I mean, when quantum mechanics is in the business of predicting something like the particle has a 32% chance of being found here when you look at it and a 68% chance of being found there when you look at it. And on any given run of the experiment, you might get either result. And in the long run, you'll get roughly 32% of here's and roughly 68% of theirs. And on pain of just not being able to reproduce the evidence that supports quantum mechanics, the many worlds theory had better justify that use of probabilistic concepts in the theory. Prima facie, they don't have anywhere to be. I mean, as you say, the equations are deterministic. There's no salient fact of which we're ignorant from a sort of third party God's eye perspective. The theory says when I make a measurement, there is a me which sees the live cat, say, and a me that sees the dead cat, or rather, there's lots of me's that see the live cat, lots of me's that see the dead cat. But none of that seems to explain why it makes sense for me to say, well, there's a 32% probability of me seeing the live cat. It kind of looks on the face of it as there's a 100% probability I'll see the live cat, and also a 100% probability I'll see the dead cat. So prima facie, there's a problem of asking even where the space is to inject probability into the many worlds theory. That's the incoherence problem. And then the quantitative problem is, suppose you did understand conceptually how probability could be in the many worlds theory. That's not enough to recover the empirical adequacy of quantum mechanics. It's not, I don't just have to recover the fact that I ought to assign some probability or other to seeing a live cat. I need to assign 32% probability to seeing the live cat. Otherwise, I won't reproduce or recover the viability of the experiments that prove quantum mechanics in the first place.
Right. And if both cases are instantiated, then how are you supposed to assign a specific
Right,
number?
exactly, yeah. I mean, in a sense, there's a slightly artificial dividing the incoherence and quantitative. I mean, insofar as we've got no good reason to assign one probability over another, you can start saying, well, did we have any good reason even to use the concept of probability?
And both of these questions are pretty obviously well motivated. Somebody should want answers to them. But my understanding is that a lot of physicists are not convinced, and philosophers. So, for instance, I spoke with David Albert and Sean Carroll recently on the show, and Sean, of course, is a many worlds enthusiast. But when I asked whether the ontological problem, though I used my own words, is the most significant problem, Sean and David both said, not at all. The most significant problem is making sense of probability. And David, of course, is unconvinced. Sean is not, though he recognizes it's still something that has to be worked on. But how do you like to answer or think that these two objections should be answered?
So I have thoughts about the way we should understand, if you like, a positive solution to the probability problem. But the starting point I'd make is that there's a bit of a double standard going on, because a lot of these conversations assume that probability is something that we find unproblematic in science generally, and which somehow runs into a special problem in the many worlds theory.
Right. But foundations of probability, just to jump in, it's still a very, very lively subject. It is not...
Absolutely. I don't think we have any inherently very satisfactory understanding of what an objective notion of probability would be in the philosophy foundations of probability even apart from the problems that come up in the many worlds theory. I mean, if you look at the kind of strategies we have for objectifying probability, for understanding what probability could be, they broadly fall into three categories. One of them is to deny the idea there are objective probabilities at all, and just say probability is just our personal metric of how much we would like to bet on something or how confident we are of something. That's probably conceptually okay, but it seems to run into a huge problem explaining the fact that we seem to make objective statements about probability in our science. We want to say the half-life of the neutron is whatever it is, 10 minutes or so. We want to say the probability of such and such medical thing is such and such. There's a huge amount of highly objective use of probability concepts in our science that doesn't seem compatible with just getting rid of the concept. Or we could say, all right, well, probability is objective. We better understand what the objective claims are about. And there's a large family of classes that in one way or another are trying to relate probabilities to something like long-run frequencies. The most popular of these days are sort of best system type approaches, but they're all in the same broad spirit of saying the kind of categorical data of how frequently something happens is the foundation of probability. And it remains deeply mysterious how the inevitably quite long-run global facts about frequency that are going on there have anything to do with our probability judgments in the here and now. I mean, you might imagine I've got to choose somehow where either I'm going to be killed if this atom decays in the next 5 minutes, or I'm going to be killed if that atom decays in the next 5 minutes. And I ask God, can you help? And God says, well, I can tell you that of atoms of atoms of this particular species, this is the pattern of their decay, this is the frequency with which they decay on average across space and time. And for atoms of this kind, this is the frequency. And I say to God, well, thanks a bundle. I didn't want to know about all of the atoms across space and time. I want to know about this atom here and now. And the reasons like that, and a bunch of more technical reasons, have made it really difficult to recover a connection between long-run frequencies and probabilities. And another aspect of that same thing is that it would be nice to imagine that probability can be identified, that in the long run, frequencies converge to probabilities. But we know the best we can do is say that in the long run, frequencies converge to probabilities, probably. And there's a kind of circularity present. And so you end up drifting to the third strategy, which is just to say, well, probability is just a primitive. You don't need to understand it in reductive terms. You just understand it. Here's how it works. It's something we have good scientific evidence for. Get on with it. Don't try to analyze it. And I think if you try taking that rather pessimistic description of the philosophy of probability, but I don't think unfair description of the philosophy of probability, and apply it in the Everett interpretation, it's not obvious that Everett does any worse than just general probability does. If you're just allowed to primitively posit probabilities, it's not clear why you can't do that in a many worlds framework. There are things you could say back to that, but at the very least, there's a version of me that say, the experiment has happened, but he doesn't know the result yet, and he can ask, well, how likely am I to see it? He can think he can ask that conceptual term, and if it's just primitive that the right thing to do there is associated with these probabilities, then again, that feels deeply unsatisfactory, but not obviously any more unsatisfactory than it would be in a classical theory. There's a whole bunch of ways in which you can reproduce the general formal claims of frequency accounts of probability in a many worlds context. And I think they're just as satisfactory or unsatisfactory as they are in the single world context. So I think it's a perfectly reasonable move to take. David Papineau is the person who I think most eloquently argued for this, to say there's no special problem of probability in the Everett interpretation. It just reminds us of a philosophical problem about probability in general. And if for whatever reason we're complacent about that problem, then we haven't any reason to stop being complacent just because we like the many worlds theory. And for what it's worth, my experience of talking to physicists is that a huge number of them have that kind of attitude. In an earlier phase of my research, I was thinking about these probability questions a lot, and I was giving quite a few talks of this to interested physicists. And my experience was it was very hard to get physicists to see that there was a problem with probability in the many worlds theory at all. And after a while, I got quite good at working out how, in the first part of my talk, I could explain to the physicists that there really was a problem of probability, so that in the second half of my talk, I could reassure them that the problem of probability was, after all, not something to worry about. And after a while, it sort of dawned on me there was a rather simpler route to the same result. And so I stopped worrying about persuading physicists how to think about the probability issue. And there are, of course, exceptions, but generally speaking, physicists seem really quite chilled about probability in the many worlds theory. That was the answer to the incoherence thing. Do you want me to... Oh, sorry, that was my sort of to Quoque kind of response. Do you want me to sort of forge on and talk about my positive way of thinking about it?
Yes, the quantitative side. Yeah, I would love that. I would love to hear that one. That one is more curious to me. How we're supposed to. Yeah, I'll let you go.
But let's be more optimistic. I mean, a different way of thinking would be, if probability is a deep problem, then never mind if it's a problem in classical theories as well. We know classical theories are false. Can we solve that deep problem or make some progress in solving that deep problem in the many worlds theory? And I think many worlds does actually have resources to help us here that aren't available if you don't have the quantum setup. And the reason for that is there's another route to thinking about probability as objective other than frequency. And the other route is to associate probability with symmetry. And you see this in a lot of the way you try to teach probability to kids. You often say, look, here's a six-sided die. How likely is it that the die will land six? And you motivate the idea that the reason it's 1/6 likely is because there's six sides. And you wave your hands in the direction of a principle of indifference or something. And of course, that doesn't really work in itself. There aren't six ways a die could land. There are continuum infinity ways a die could land. If I painted five sides of the die green and one side red, and I asked, how likely is it to land red? And you said 50-50 because it could land green or it could land red, principle of indifference. That's pretty unsatisfactory. If you interrogate those kind of arguments, what you really find going on is some kind of symmetry principle. There's a symmetry between the six faces of the die, such that with appropriate assumptions about the dynamics, you somehow the uniquely appropriate probability distribution to put along the way the die could land is one that respects the symmetry. The problem with those arguments in classical physics is that if the underlying physics is deterministic in single universe, something's got to break the symmetry, because the die actually does land one side or another. If I had a completely symmetric initial state of the die and completely symmetric dynamics for the die, or I should really say if there's a symmetry of the dynamics such that the initial state is perfectly symmetric under that, then it can't land one side rather than another. The symmetry argument would tell you if it was going to land one side, it would also land the other side. There's no indeterminism. So the only way the die can land one way rather than another is if actually the initial conditions break the symmetry, if something specific about exactly how the die was thrown is affecting what's going on. And now you start saying, well, I'll put a probability distribution over those initial conditions, but now we've got to regress, and we still haven't understood what probability is. So symmetry-based ways of understanding probability run into trouble in a classical universe. But in a quantum universe, that argument I've just given, that something must break the symmetry because one thing happens rather than another, isn't available. Because it's not the case that one thing happens rather than another. In a quantum universe, all the things happen. And so my outcome state of the quantum mechanical version of throwing the die can be perfectly symmetric. Each of the individual worlds is not symmetric, but the overall collection of worlds still respects the symmetry. And so you've got the resources to use symmetry-based arguments to motivate or even prove the idea that we should apply probabilities and to particular sorts of probabilities in the many worlds quantum setup. And you've got some prospect of actually deriving probabilities from more categorical features of the system, the symmetry features of the system. And there's a tradition of trying to do this that goes back most of 30 years that David Deutsch was instrumental in setting up. And the way those arguments have traditionally gone, certainly the ways I developed them a lot in the 2000s, is to operationalize the notion of probability in terms of my decision-making, so as to solve the problem of incoherence, and then ask what strategies could I adopt in a many worlds framework. So what I mean by operationalize it here is something like, I'm going to toss a coin, make a quantum measurement, let's say, and you're going to give me a big wad of money if one outcome occurs, and I get to choose which outcome I get the money on, but I have to choose before the experiment's carried out. So Obviously, one strategy I could have is I get the money if the result is the particles here. Another strategy is I get the money if the particles there. And it perfectly well makes sense to use some of the ordinary tools of how we think about probabilistic decision making to say the kind of strategies I could have here end up being quantified as having the same operational structure as assigning probabilities and betting according to those probabilities. There's a lot more to say there, but basically you're carrying over a lot of the machinery to from ordinary decision theory into the quantum setting. And then you can ask, okay, what strategies should an agent carry out? And roughly speaking, if you constrain the agent to adopt strategies that respect the symmetries of the quantum theory, then that uniquely forces the agent to adopt a strategy that's operationally equivalent to the usual quantum mechanical rule. And then if you consider agents whose strategies don't respect the symmetries, you can start showing that those agents' behavior starts getting inconsistent over time in various ways. So an agent ends up in temporal conflict with their other selves. And the reason for that is sort of if there's a symmetry, then you can sort of permute, there'll be quantum mechanical operations that agents shouldn't care about that permute possible outcomes. And you've got the literature for this has got quite complicated. And it's generally described as various decision theoretic proofs of the quantum probability rule. And that description isn't unfair exactly, but I think sometimes it hides what I take to be the really deep philosophical insight that lets us try to solve the probability problem in the many worlds theory, which is that symmetry-based arguments for probability have traction in a situation where everything happens, that they don't have in situations where only one thing happens, and so something has to break the symmetry.
A few things. First, did you study with David Deutsch? Or do you still work with him on these sorts of issues?
I didn't formally study with David. I was directed to him by my undergraduate physics tutor, Erhardt, who's a close friend of David's, when I started asking awkward questions about the quantum measurement problem as an undergraduate. I had a bunch of chats with David as an undergraduate and grad student in Oxford. I had an early draft of his paper on quantum probabilities. So his work had a very substantial influence on me at certain phase of my career, but I would never formally work with David. I mean, David is kind of quite independent-minded as a scholar. He has an affiliation to Oxford, but no formal faculty position there. He doesn't formally take students. So people who end up working with him always end up working with him in a somewhat informal capacity.
Mm-hmm. And then the other thing at more higher level, but I think that some of the language that you use, so agency, decision theoretic, it points to maybe a broader conclusion that can be drawn out of what you said, which is that in this deterministic story, you replace, or one of the struggles or attempts is you're trying to replace objective probability with subjective probabilities. Is that on the mark at all?
No, I want to resist that quite strongly. Although it's a reasonably common, I'd say, misreading of how this literature runs, although this is a contentious question. So the way I would generally think about it is that in modern philosophy of probability, we have a kind of dual notions of probability. We have a kind of subjective, creedal, decision-influencing notion of probability. And then we have some objective quantity that's supposed to be either posited primitively or extracted out of the physical goings-on in the world, an objective chance in David Lewis's terminology. And then we want to establish a certain kind of cohesion between them, such that effectively agents try to conform their personal probabilities, their credences, to these objective probabilities, these chances. And then you have a bunch of philosophical questions about just how that's supposed to go. And I want to say that the thing that plays the role of objective probability in the many worlds theory is the quantum mechanical weight of the branches. That's a perfectly objective quantity defined inside the quantum formalism. It was perfectly well defined in the early universe before there were humans. It'll be perfectly well defined after there were humans. And it's then a substantive claim that the way that quantity plugs into our epistemology is that rational theory testing strategies treat that quantity the way we treat probability in more single world stories. But I don't think that eliminates the notion of objective probability. In fact, if anything, it discovers what the thing in the world is that's the objective probability. Having said which, there's a bit of semantics about this. If somebody wants to say, look, what I mean by objective probability conceptually and analytically requires a single universe, well, you can't argue the definition. If that's the position, then sure, there is no objective probability in the many worlds theory. But there's a different objective thing. Mod squared amplitude is an objective thing. It has the same formal mathematical properties as probability in the decoherent regime. It's in no way subordinate to us in any sense. It's perfectly well definable without bringing agents in. The only point at which you need to bring agents in is if you ask how we could experimentally test claims about it. So that kind of bifurcation of an objective probability-like feature of physical reality and the way we as agents interact with that, I'd say is going to happen in a many worlds account of probability, however you set it up. And I think it's fundamentally pretty similar to the kind of setup you have in a more philosophy of probability single world setup, where you might, for instance, be trying to recover your objective chances as long-run relative frequencies, and then trying to solve the philosophical problem of how those quantities are to be related to our personal decision preferences.